guys have from, so any questions about how to identify a certain type of transformation? Do you guys feel pretty comfortable with it? Okay. So in your note guide, I don't understand. Sorry. I'm like, okay, in your note guide, we are going to look at the very first thing kind of organizes. I'll bring it up to show you guys some different ways to write quadratics. Those of you that don't have a note guide, you take the notes wherever you're taking your notes. However, we go through what I'm about to talk about, you can write down nothing, or you can write down what's pertinent to you. We're basically just going to give an overview of the different ways you could be given a quadratic equation and kind of some ideas of putting together different vocab they would use and different ways that we would come up with these formulas. Should we start with finding the vertex point? Does this type of equation give us some other information? So just an overview of what's important parts about the parabola, how we could find them, what's necessary when graphing, or otherwise, okay? So we're going to look at standard form, factored, or intercept form, and vertex form. Or you don't have to write down anything. You can just listen to the overview. It's up to you guys. So most of this stuff is found in chapter 4. So I know the last unit, it was a little bit like kind of selections from different parts of your textbook, or not in your textbook, certain parts of it, because that's still part of our curriculum. However, this is mostly from chapter 4. So big idea about quadratics in general, they make a parabola, okay? So anytime they ask you any of these words, they are talking about the same thing. So x-intercepts, our roots, our solutions, our zeros. Those 4 words mean the same thing. They mean the place where the graph is crossing the x-axis, or the solutions to the equation, okay? Do we need to absolutely have those values when we're graphing? No, because it's possible that we might not even have them, right? It's possible that this whole graph could be shifted up 10, and then it wouldn't even cross the x-axis. So it's not necessary to graph the intercepts every time. Sometimes it's convenient, and sometimes it's not. If it's not convenient and you're just trying to make a graph, sometimes it doesn't help me to get 2 plus rad 5 over 3. Like, I'm not probably as good at graphing that point as I am graphing like 2 comma negative 1 or something like that. So just be aware that those are what they're called, and it's an important part of our parabola, but we don't always need to graph that part, okay? Other important parts that we will have to know in order to get the graph of our parabola, we need to know generally where our axis of symmetry is, and on that axis of symmetry, very slowly right here, dramatic pause, okay, sits our vertex point. So you definitely need your vertex point to have an accurate representation of your parabola graph. Otherwise, we don't know exactly where it turns around, okay? So one way that we can be given the quadratic is in standard form. What are the ways that you guys solve an equation if you were given standard form? So let's say the question wasn't to graph, but it was to solve a quadratic, and somebody laid in front of you like 2x squared plus 5x plus 3 equals 0. What are some strategies? Chris? Okay, so one way is to use the quadratic formula. Ray? You can factor it. Okay, anybody know another way? There's called completing the square. Yeah, so we're going to talk about all of those in this unit and make sure our skills are pretty solid, and then we can use them in more complicated situations. So if it factors, we'll often factor and go for it. If it doesn't factor, we either complete the square or use the quadratic formula, which we'll talk about later, might technically be the same thing. They just look a little different as you do them. So let's say I went and did the quadratic formula. What does the quadratic formula find for me when I have solved it? Which part of the graph would I be solving for? Yeah, what part of the graph is represented by your solutions we just talked? Alex. Yeah, the x-intercepts. So that's what you found, the solutions, the x-intercepts, the zeros. Now, I'm not saying that's the best way to go about it, but that's what the quadratic formula would find you. Are those necessarily going to be really convenient numbers, especially if it didn't factor? No. So are those necessarily something I want to graph? No. Okay, so actually when it's given to me in standard form, I usually don't start by finding the solutions unless it's factorable real quick. Does anybody remember how you find the axis of symmetry if they've given you the equation in standard form? Emma? Negative b over 2a. Good. But here's the amazing thing. Let's say we did find these points, whether they were convenient or not. Would you guys agree that 2 points that are on like the same level of your parabola, that the axis of symmetry is directly in the middle of them? So if I pick 2 points, if I found the middle of them, I would be lined up with my axis of symmetry. So I used to think in Algebra 1 that somebody created all these random formulas, that they just decided things should work that way, and then we all kind of like did it because that's what they said, because they were the formulas. However, it's quite amazing, and I think in Algebra 2 you guys should try to develop a sense of this, that all these formulas actually came from something that they were doing over and over again, and they were like, oh, instead of doing this over and over again, can't I just make a formula for it? And so then they would make a formula for it. So the quadratic formula actually comes from a different process that they were doing over and over again, and they were just like, I'm just going to sum it up in this one thing every time instead of going through all these steps. Just plug the numbers in here. And this other formula we're going to talk about that Emma just pointed out to us actually came from this idea. If you wanted to find the middle of 2 numbers, what mathematical process do you do? Chris? You take the average. So on the backboard, I have averaged our 2 solutions from over there. It looks horrible, but it works out so beautiful. So I averaged both of the quadratic formulas. So I added them together and divided by 2, and it looked like it was going to be horrendous, right? But when I add together the 2 fractions from the quadratic formula, they already have a common denominator. The radical parts cancel out because they're the same thing, a positive and a negative. And the 2 negative b's add up to negative 2b. So I have negative 2b over 2a. And then in averaging, you add them together and then you divide by 2. Okay? And if you go through that dividing by 2 process, it basically just cancels out that 2 that was with the b's, and you get this negative b over 2a. So somebody didn't randomly make up this formula. They were like stuck back in the day, right, before they gave us this formula. They would be doing something like this. Like even if these weren't real solutions, finding these and then averaging them, you can only do that so many times and probably get pretty annoyed, right? So then why not come up with this nice, much smaller formula? So if I was being asked to graph something in standard form, I would not start with the quadratic formula. I mean, it would give me, sorry, back people. It would give me solutions, but it wouldn't give me necessarily a good part of my graph. I would start by finding where the axis of symmetry is. Okay? Because once I know the axis of symmetry, what else have I found by finding that number? So let's say it's at 3, like it kind of looks like in this graph. I know that this line is x equals 3, but what else do I know right now then about my graph? Right? Good. The x value of the vertex would also be 3. And then how do you find a y value of a point once you have an x value? You plug it back in. So this is super weird notation, right? But it's just saying this number is going to match what you got from that formula, and it's going to give you the x number. And once you have the x number, you find the y number by taking that number and plugging it back into your function. Okay? So this is where I would start in standard form, right? There's a small formula that gives us this. And then how would I get points on the side? I can go find the solutions. Might not always be convenient. I can just plug numbers in after I know where the axis of symmetry is. Once I know that everything is kind of centered at 3, then I could plug in some numbers not so far from 3 and get a good shape of my parabola. Does that make sense to everybody? Okay. All right. Second way that we're going to see it. Okay. If it does factor, factoring is extremely useful and is very quick at finding solutions, right? So I'll be honest, if it does factor, I would probably use the factors to come up pretty quickly with a couple of points on my graph. So again, what am I pointing out to you here? Don't memorize all these things. We want to understand how all these things are related. This idea that any 2 side points on the parabola that are at the same level, I can find the middle of the parabola by averaging them. Or there's a formula that might help me find the middle of the parabola, and then I could plug things in to get side points. So if it was factorable, I might factor it, and I might actually find the solutions, because that's a pretty quick way to get a couple of points on my parabola, right? if I did start like this and I had points on the sides of my parabola, but I didn't yet know where the middle was, how would I find the middle once I had plotted those points on the side? Average them, okay? So what I'm giving you right now is not a formula. It's an idea that we're discussing right now, that if I'm able to plot 2 points on the side and I can get those, the next thing I would do is average them to find the middle, okay? And just like we talked about before, once you have found the middle, the axis of symmetry, not only have you found the equation for the axis of symmetry, but you have also found the x-coordinate for your vertex. And once you have the x-coordinate of the point, how do you get the y-coordinate? Plug it back in, okay? So we're just trying to build an idea here that there are some forms where there might be a formula or something about the equation that gives us the middle very quickly, and then we'll build the sides. Or in some cases, you might be able to find the sides very quickly, and you should be able to average them and get the middle. We just want you to be able to decipher different useful things about different forms of the equation. Haley? Yeah. So it just means, like, let's say this came out to be 1.5, just because that's what it looks like on the graph, right? So my axis of symmetry equation would have been x equals 1.5. 1.5 would be the x-coordinate of my vertex. I would take 1.5 and plug it in for each x in the equation. The a's, p's, and q's would all be numbers. And then I would calculate what the y value is from the equation. Is that okay? All right. So last format that we're going to look at it in is vertex form. So notice the setup of vertex form. What does this look like? It's got those things, right? So, and again, does it really matter that I used the letters A, H, and K? No, some other books might use other letters, okay? What matters is they're set up in positions that are exactly how we've studied them before. That inside the squaring is like an x minus a number thing. And then outside the squaring, there's like a value that's multiplying and a value that's adding. Anything that is set up this way is going to do to the quadratic exactly how it affected the absolute value function and how it affected the step function, right? Which means, anybody have an idea about if someone gave me an equation in this form, what would be the first automatic piece of my parabola that I could get really quickly? Kristen? Good. The vertex is h and k, just like the absolute value function, because every parent function has that vertex at like 0, 0, and then h and k are my only things that shift it up and down to a new location or left and right. So I can immediately get the vertex at h and k and the axis of symmetry that goes with it, since it's lined up with the x-coordinate of that vertex. Okay? Then you would have to get some side points. So this doesn't really do it justice. It just reminds you again that there are x-intercepts. Do you have to find the x-intercepts? Not unless you're asked for it. So if I ask you for a table of characteristics, I'll probably ask you for it. But if I don't, then I don't. And you don't need those points. But you need some points to build in the correct shape of the parabola. And we're going to have 2 ways that we can do that. What's one way that we can do it from like algebra 1? How can we always get points on a graph? Chris? XY table. You can always plug stuff in. Now be smart about your XY table. Center it around the right thing first. If you don't have the HK, you're not going to get a good representation of the parabola. But once you have that, you could just plug some stuff in around that H value, okay? Other way is through transformations, and we're going to look at that today, okay? Like we were able to graph the absolute value function without making a table, right? We were able to get the graph very quickly by knowing the shape and the behavior of the graph. We were able to do the same thing for the step functions, right? Just knowing the shape of the parent function, we didn't have to make a table, and very quickly, by understanding what each number does in the equation, we could create a new step function just by knowing the parent function really well. We're going to try and do that same thing today with quadratics that go into this form, okay? So today is going to focus on this form, but we're also going to have a b value in there still where we can do horizontal stretching and compressing. And then tomorrow we're going to focus on the standard form, where it doesn't look all nice like this and have everything in the perfect position for you to immediately find the vertex and all of that stuff. Okay? Is this all right with everybody? Yes? Okay, so we are going to use this Cartesian catalog again. So remember, these are things that are like your notes. They go into your portfolio. Okay? They basically provide us with a huge graphing reference, right? They take each function that we study, they put it on one paper. They have the parent function and examples of that function and all the characteristics of that function. Okay, so that's going to be our goal. Let me pause here for a minute. Okay, so we're going to build the parent function first. We're going to get the table on here, and then we're going to let you guys fill in the characteristics, okay? So the table for the parent function is going to be really important to us. It was like knowing the step function graph. Try to remember, when we were first building the tables, it was like pretty complicated to explore what was happening, right? We could kind of establish a pattern, but we had to plug in a lot of like in-between numbers, make sure that we got something right. Once we established what it looked like, having that picture in our head, we just had to know like a starting point and some of the transformations, and we could quickly make a new version of the graph. So we're going to try and do that now. The difference is, since everything's not a step function that we know is just like steps that are a certain amount long and a certain amount apart, there is a different complication to it. However, we can address it if we just know the parent function really, really, really well. So parent function, remember, is the most basic function. Who thinks well, I'm not even going to ask because it's up here, because that would be a dumb question for me to ask, right, because they answered it. So the parent function is like we're studying quadratics. Quadratics square things. So the parent function is just taking x and squaring it. Nothing else, just applying the function that you're trying to study. So if we made a table of values for the function that is just x squared, we would have 0, 0 as our vertex. That would be the point where it turns around, because negative values will get squared and they'll turn into positives. Positives will get squared and turn to positives. So 0 would be the turning point. So 0, 0 would be our vertex point, and then we'd want to explore values on each side of 0 to get a good idea of the shape. So I'm going to plug in -1 and -2 and +1 and +2. And then remember, you're just squaring it. So I square -2 and I get -1, I get 1. Square +1, I get 1. And I square +2 and get 4. So here's where we want to get. We want to get where we are with absolute value function and with step function, or where we should be. When I write down an absolute value equation with absolute value bars, what's the first picture that pops into your head? What do you picture it looking like? Yeah, immediately, a V, right? We know absolute value bars means it's shaped like a V. And then we know some very basic things about that starting parent function. Its vertex is at 0, 0, and the slope of the lines was 1, right? Step, we have the same idea. You see those brackets, what kind of picture pops into your head? The steps, right? The stairs. And we know starting point at 0, 0, go towards the right, 1 over, 1 up for our parent function. Right? We have these pictures in our head. We want this table of values and an understanding of what a parabola looks like in our head too. So every time we see a squared function, we want to think parabola, and then we want to know that in its most basic format, it has this vertex at 0, 0, then it has these points that when you're 1 away horizontally, you're 1 above, and when you're 2 away horizontally, you're 4 above, 3, you're 9 above, etc., where you're squaring each of your options. Okay. So we have this parabola. What is our vertex, our HK? Let's fill in the details here. 0, 0, and I can't really fit it on the thing, so I'm going to write it over here. Okay, so your vertex is 0, 0. What are your x-intercepts and y-intercepts? 0, 0. Parent functions are really simple, right? They don't complicate it too much. So these are also 0, 0. What is our domain for a quadratic function? All real numbers. Good. We can plug anything in and we can square it. Okay, we might not be able to get everything, because when we square our most basic function, notice here we only got positive values as results. But you can plug any real number in and you're able to square it. So our domain for all quadratics should be all real numbers or -∞ to infinity. Okay. What about our range for this one, Helan? Good. Y is greater than or equal to 0. If we're writing that in interval notation, it hits 0 and goes towards infinity. Okay. Minimum of 0, maximum of infinity. All right. Increasing, decreasing intervals. Who thinks they can give us the increasing interval? Chris? Good. Do you guys see this part as the increasing part? But remember, when we write it, we're writing as domains, x's. Which x's is it behaving like an increasing thing for? From 0 till infinity. We're not saying it's going towards infinity. We're saying for the x values from here over, it behaves like an increasing type of thing. Okay? So increasing interval from 0 to infinity, and you can use either bracket on 0 that you want because they're kind of indeterminate about it and they accept both. Because 0 is like the turning point, so we don't know whether to include it or not. Okay? All right, what about our decreasing interval? How would we write that? Hunter? Good. Negative infinity to 0. Okay. And again, a lot of people keep asking me, shouldn't you say positive infinity? Because even though it's decreasing, it's going from here to here. I'm not talking about where it's going. I'm saying the part of the graph that you would label as decreasing is in the domain from negative infinity to 0. Okay? Or for the x values from negative infinity to 0 is where the graph is behaving like a decreasing thing. So this is listing the x's where we see a decreasing portion of the graph. All right? Is the graph 1 to 1? No, right? Same as absolute value. It passes the function test, but the inverse of that is not true. Okay? When we pick a y value, there's always 2 x's because it has that turning point and goes back. So not 1 to 1. The rate of change is not something we're going to discuss with the quadratic. It doesn't have a constant rate of change. So if we want to list a rate of change, it would have to be changing constantly with the same amount, like an absolute value, because it has linear sides. The minute you're not linear anymore, every time you go over 1, you're going up a different amount. So you can't label one constant rate of change. What is our axis of symmetry for this quadratic? David. Thank you. Okay, minimum value, maximum value. Okay, which one does it have? A minimum value in this case. So maximum value is just none. You don't need to tell me it goes towards infinity. I'm asking if it has a specific value we can identify as a maximum value. We'll just say none. Okay, what is the minimum value? 0. And we're picking the y value of the vertex point. Okay? The y is what we're discussing when we say value. And then the asymptotes are not something that's applicable for this function. It doesn't have asymptotes. Aria?
Why is the minimum value when it only has 0 instead of parentheses 0?
Okay, so 0, 0 is the minimum point. But when they say the word value after it, they're just referring to y values, like the range type of thing. What's the highest number or the lowest number that your graph reaches vertically? If they say, where did the minimum occur at, they would be talking just about the x value of the minimum. And when they say just the minimum, if they didn't have the word value there, you could include the whole point. But the word value makes it really specific to like the actual maximum or minimum height vertically that it's reaching. Is that okay? Okay. All right, any other questions about our characteristics for the parent function? Okay. So then let's look at a more difficult example. So we're going to look at the one on the back side, okay? I'm going to size it a little bit. I have it written on there. I'm going to rewrite it up here, and then we're going to rewrite it even again. So you have a -2. If it printed weird, it should be a negative if it's not there. Then you have crazy stuff in the parentheses being squared, right? And then +5. First thing we have to recognize is that we can keep a b value inside of that squared because we now know how a b value behaves, right? A b value is going to cause what kind of transformation? Elin? Good. Horizontal stretching and compressing of our graph. So I understand having something there, so I don't need to move it from there. It can exist in there. However, remember our h value is only truly doing what we think the h value does, shifting it left or right, if you're just looking at a quantity that is x minus h. That's the only way we've studied it, right? If you put a different number in front of x, you're not going to see the same shifting that you did before. So we need to rewrite this every time there's a b value there, so that value is just kind of separated from the x minus h group, because we've only studied that group as exactly that, x minus or plus a number. So we don't truly understand what's happening with the +1 up there. We don't know, we think we know how to interpret it. We want to be like left 1, but It's not actually left 1 because that's a third x minus h, and that's not how we studied it. Okay, we only know how to interpret it if it fits this very specific format. Okay, we didn't study 12 formats. We studied 1, and we have to transform our equation into that format if we want it to do what we think those numbers do. Okay, so what would be in this set of parentheses here if I've factored out a 1/3? Now, when I say I factored out a 1/3, I mean out of those two terms, not completely out of here because it's being squared and all that stuff. Quinn? Good. There's two ways for you to know 1/3 times what would have made 1. Or remember, when you factor something out, you're dividing that number out of the number that was previously there. So you had a 1. If you take the 1 that was previously there and divide it by 1/3 and go through your fraction operations, you'll get 3. Okay, so if the fractions bug you, write it off on the side of your paper and go through it really thoroughly to make sure you're getting the right value. Okay? All right, so now let's talk about the transformations that are happening here. This negative right here, what type of transformation is that going to cause? A reflection over the x-axis, right? So the negative is actually affecting y values, right? It's a vertical kind of change, but when you change things vertically, you flip over the x-axis. What is the 2 going to cause? Looking for someone new that hasn't talked to us yet today. Ready to talk to us too? Haley. Okay, good. Okay, so vertical, it's still a vertical, and how far they are away from the axis, so it's stretching or compressing its original position to get further or closer to the x-axis, okay? What's the other vertical transformation that's up here? Jason? Good, the k value, the +5, and that's going to shift us up 5. So our y coordinates of our points, just the y coordinates, because remember, the y coordinate's kind of independent of the x. The x goes horizontally, but then the y has been put somewhere. But if you stretch it or compress it, reflect it or shift it, you're not changing the x at all, right? You're just changing the y. So the y values are going to get multiplied by a negative to reflect them. They're going to get multiplied by 2 to stretch them further from the axis than they were originally, and then they're going to get 5 added to them to move them up. So essentially, every y coordinate that originally existed in the parent function is now going to have this happen to it, and it will take its original measurement, like if it was 1, meaning 1 above the x-axis, it will reflect it, it will stretch it, and then it will shift it if we just do this arithmetic, right? 1 would get turned into -1, and then multiplying by 2 would turn it into -2, stretching it further away, and then adding 5 would shift it up to that position that it has to be in. Is that okay with everybody? So the cool thing is, not only can we do the transformations visually, but we can also do them with arithmetic on the points, because a point is literally measuring how many units you moved away from something. You can now change that measurement just by doing arithmetic and know the new place that the point should go. Okay? And you can do the y separate from the x, because the y will just adjust everything measured from this axis. The x is doing a different measurement, so we can do it in a different step. Okay? What's happening horizontally? And horizontally is more difficult. That's why I did the vertical ones first. Emma. Good. So when you see this, it says 1/3, but we studied this, right? It says 1/3, but what actually happens to the graph? It gets like stretched out longer, right? Basically, by the reciprocal of that, it would be 3 times longer than it was. So if I want to show that, I don't multiply x by 1/3. I actually am going to multiply the x distance by 3. And again, how do I know that? Because we studied it by doing these investigations and saw what happened over and over again to the graph. And we understand that 1/3 has a meaning in the equation, but as far as the measurement on the graph, it's the reciprocal of what we're seeing there. It's actually getting stretched 3 times as long, so I want to multiply that x distance by 3. Okay? And now this says x 3, but what's actually happening there? Good. So we study this as a minus h to try and make it work the way we want it to work, is basically why they put the minus in that general formula, right? So x plus 3 actually means it's x minus -3. The -3 is telling us what's happening to the graph. The graph is actually going to get shifted left 3. To shift a point left 3, what do you physically have to do to the x value of that point? Subtract 3 to move it left 3. So I really want to point out to you that the stuff I'm writing right here that I can do to the graph is not just taken straight from the equation, right? It's like this. Here's what the equation says. This is the type of transformation that means. Here's how I do that transformation with arithmetic. The y one happens to look exactly the same because the y value was really straightforward as to what was happening to it, right? But the horizontal stuff was like blowing our mind. It was all like the opposite of what we felt like we were seeing there. And so that's why you're seeing different operations here than you're seeing right here, because we need to say what's going to happen to the distances on the graph. Ariane? So remember, this is x minus h. So the h value has to be negative 3, which means our graph is moving left 3. And to get a point to move over to the left 3, I need to subtract 3. So again, this table is not just pulling things straight from the equation. It's interpreting the transformations, right? Here are the transformations that are happening. For y, it's really easy because it looks just like they look in the equation. And for x, it won't because of the different things we saw while we studied them. That like we put in a number, we saw a consistent change, but the change wasn't what our eyes probably originally expected by putting that number into the equation. Kaylee? So the okay, good. So the exponent's not included here because I'm going to use the parent function table. So we already made a parent function table, right? On the other side. What did the parent function do to get x turned into y? Emma? Right, and we got those values by squaring it, right? So if I use the parent function table that was already made, I have these before values became these things when they were squared. So I've already squared them in the parent function table. So you guys have it on the other side. I'm going to write it right here to remind us. So we have this that already addresses the squaring. So this would make the parabola shape on the graph. And now I'm just going to adjust the points from that thing that's already squared. So the squaring is accounted for because I'm starting with that table and I'm not starting from scratch. I'm starting with the parent function that already makes that parabola shape and squares everything, okay? So now I'm going to take every x value from that table, and I'm going to multiply it by 3 and subtract 3 to make new x values because that's what's happening to those things. They're getting stretched and then shifted to the left 3, so I'm going to do that to them right now. So negative 2 would become 3 times negative 2, which is negative 6, minus 3 is negative 9. So the point that used to have an x-coordinate of negative 2 will now have an x-coordinate of negative 9 because of the way x is being transformed. Is that okay with everybody? And then I'm going to do the same thing for each x-coordinate from that table before. So negative 1 will become negative 6, 0 will become negative 3, 1 will become 0, and 2 will become positive 3. Is everybody okay with where I'm getting that list of values? Okay, so that parent function is imperative. If I don't have that, I can't do this, right? Because that's the only way I knew that x originally went with this y, and now this distance is going to be stretched and moved to the left. Well, this one's being stretched, reflected, and moved up 5 or whatever, and then they can still remain a pair, but I can see what's happened to their values, okay? So now I'm going to do the same thing to y's. All the y's are going to get reflected, stretched by 2, and moved up 5, okay? So that 4 that originally went with negative 2 is going to be a new number after these transformations that now goes with negative 9 because that's what happened to the x's or the horizontal distances.
How do you know it's negative 2?
I'm using my parent function. I mean, you could have used anything in here, but you have to use stuff that originally came from the squared function or you won't get a parabola graph.
So would it be different if you input it like negative 1?
So I put in negative 2, negative 1, 0, 1, and 2. I took every x coordinate in my list and I did these things to them. But I have to start with a list that is from the squared function.
For the negative 2 bar.
Oh, from the function right here, because there's a reflection and a vertical stretch. And so that's where I'm getting that part. Is that okay? Okay. So now I'm going to take all the y values and do this to them. So negative 2 times 4 is negative 8, plus 5 is negative 3. So that 4 will be transformed to negative 3 once you reflect it, stretch it, and move it up 5. Okay? So this is just kind of a quicker way than me doing all those physical things on the graph. You can do the physical things on the graph. It just takes more steps and a little bit longer. And so then we're going to go through the whole thing and do them. So we'll plug in positive 1, 0, 1, and 4 again. Now I'm going to plot these points. It should make sense when I plot it, meaning what shape should these points make? A parabola. Where should the vertex be? What's my HK? Negative 3, 5 should be where the turning point is, okay? So the vertex should be transformed into the vertex. That should match what we know about H and K. So there are a lot of kind of checkpoints here where you should see if your graph makes sense. It should face downward because of the reflection, right? There are some things I know that these transformations cause that should make sense when I go to graph them. So let's go ahead and graph these points and see if we get something that makes sense. Sorry, my sketching leaves some work to be desired. All right, so let's look at it. Does it make sense? Is the vertex in the right place? Do you have a vertex at negative 3, 5? Yes, okay? It should face downward because there was a reflection, specifically over the x-axis. In this one, if there's a reflection over the y-axis, does it even matter? No, because symmetrical on both sides. But it should face down because of that reflection. And then 2 different stretches happened, right? It got stretched vertically, which would make me think it gets narrower, which I don't really see here. But I think that's because it got stretched vertically, but then also what happened? It also stretched horizontally, right? So it got would have made it more narrow, but then it this way, okay? And does that make sense with what you see on the graph? Does it look like that could have happened to the parabola, that all those things are incorporated there?
So, it was stretched vertically by a factor of 2, but then it was expanded horizontally by a factor of 3, so the 3 outwards.
Yeah. So it actually went more distance this way, so it actually got a little bit wider, okay? But the points spread out in general because we had this and this happen. Okay, but you should be able to see each of those things kind of happen in your graph. The visual that you get at the end should make sense with the transformations that you felt like you're seeing happen with the numbers in the equations. Is this okay with everybody? Okay, so the table just gives us a kind of quicker way. We could have graphed the parent function right here, and then we could have flipped all the points over. Then we could have stretched them all out by 2. Then we could have moved it up 5. Then we could have stretched them all by 3 horizontally. And then we could have moved it to the left 3. And we would get the same thing that we got here. This just does it a bit faster because it does all the arithmetic for you at once instead of you having to physically move them around on the graph.
Did you get this
From the 1/3. Okay. So remember, 1/3, but we know from our investigations that actually stretches it by a factor of 3. And we have to express here what's physically happening on the graph to the distances. So if the distances are getting stretched by 3, then we want to multiply them by 3. And that's why we start with our step function, because that's the function that you can see the clearest what's happened horizontally versus what's happening vertically to give us a really good picture of what each number is really doing in the function. And then lucky for us, that pattern continues with each of the functions that we study. Okay, so if we learn this really well at the beginning, we just have to learn a new parent function every time, but then we should be able to do this fairly quickly because all the transformations will stay pretty constant. Okay? All right, and so then we're going to go through, I'm going to have you guys fill in characteristics, and then we'll check them tomorrow, and we'll start with the other thing on this as our warm-up. But before we do that, I want to talk about the x-intercepts, because I feel like that's going to be where you guys struggle the most. So, I just want to make it, here. All right, so let's talk about the x-intercepts of this function. So you can work right there, have the equation in front of you. So we know that to find x-intercepts, we set y equal to 0. It doesn't matter if you use how we like factored the b value out from the h value. You can use either one. I just think like in solving, it's less work to work with the original one than to have that extra set of parentheses in there and stuff like that, okay? And then remember, you're looking for an x-intercept when you're doing this. Lucky for you, and this is lucky whether you think so or not. There are other things about this problem that are not so lucky, but all of the x's are already positioned inside of there. So there should be no motivation for me to go multiply that out and actually square it, because all the x's are already nicely confined in there. If there was another x somewhere else, I'd have to multiply this out because I need to have that x join the group, right, to try and like eventually get x alone. But if all the x's are already in this group, I don't need to do that. So what I would want to do first is isolate the group that has x in it. So I would want to subtract 5 and then divide by -2. Is everybody okay with those thoughts? And that's what I would want to do. Okay, so after you do that, you should have something that ends up looking like this. Okay. And now, what do we want to do? Because we eventually have to get x like out of that quantity and then by itself. So what are we going to do to get rid of the fact that it's like in this squared type of thing? Ellie? Good. What's the main thing we have to remember if we're doing a solving process like this and we square root both sides of an equation? Plus or minus. And so for those of you that are struggling with why it's plus or minus, not every radical, if I say what's the square root of 4, your answer should just be 2. That's it, not plus or minus 2. The square root of 4 is 2, positive 2. Why am I putting plus or minus here? Because here's what you've had. They squared something and they made this positive number. So that's like me walking in and saying, you guys, I squared a number and I made 4. Which number did I square to get 4? 2 or -2. If you start with only knowing that somebody squared something and made this answer, they could have squared a positive or a negative to make that answer. Does that make sense to you? So if you're solving it from a perspective of, oh, I know something squared turned out to be this, you have to acknowledge when you get rid of the squaring that the number they had before they squared it could have been positive or negative to create that. It'd be -5 over -2, and so then it would be, is that okay? Okay. And then we would just work on getting x alone. So we would subtract 1. It doesn't look pretty, but it is what it is. Okay, so we'd have like 1/3 x equals -1 plus or minus this really gross radical. And then we would times by 3. Is everybody okay with how I'm making those choices? I'm focusing on isolating x, okay? So I would times by 3. So x would be here. When I times this by 3, it would multiply to both terms. So I'd have -3 plus or minus 3 times this radical. And then probably the only thing wrong with that is that like we left the irrational number in the denominator. I don't know, sometimes people will care about that and sometimes they won't, but most of the time they won't leave an answer like this. So to make you aware of the other format, remember how you would rationalize denominators, that you would multiply the bottom by rad 2 so that you could get that to be a 2. But in a fraction, if you want to keep it the same value and you multiply a factor into the denominator, you also need to multiply that factor into the numerator. Those would be my x-intercepts. Yeah. Thank you. Good. Okay. Are we okay with the general process of that? So when we square root, if it's written in form and you're finding the intercepts, you're going to use radicals to solve it, right? Because all your x's are nicely contained in the square. But when you use that radical, you have to remember plus or minus. Then just do the normal arithmetic you do to get x alone. It might look ugly. We have to deal with that. And then just don't leave a radical in the denominator. Okay? And so then what we will do when you guys come in tomorrow is we will go back through this